Hello everyone, I am Pragya Srivastava. I am here to record a lecture on lithography and the concerned subject is VLSI technology. The course code is KEC053. So lithography is a word which is derived from two different words, which is lithos and graphy. So we need to understand what is the meaning of these two different words, lithos and graphy, and also we should know that why do we do lithography and how this lithography process will help us when we are actually trying to go for IC fabrication. So lithography or photolithography is a process of transferring geometrical pattern from a mask to the silicon wafer. So what actually we are trying to do? We are trying to transfer a required pattern which we are already having, and we are trying to transfer this pattern on the silicon wafer. So transferring pattern on silicon wafer, with this I mean to say that we are having a set dimensions, and on that set dimension sometimes we want to add a dopant and sometimes we want to remove certain layer. So let's say I want to remove a layer of silicon dioxide, and at that point of removed silicon dioxide I want to add some dopant, p type, n type semiconductor. So lithography will help me when I talk about removal of some specific layer from specific point, from specific dimension. These regions where the dopants have to be incorporated is selected and marked by the process called lithography. Lithography, or sometimes it is referred as photolithography. So lithography, we can have like multiple kinds of lithography. Sometimes it is photolithography and sometimes it is electron beam lithography, and we also have optical lithography. So everywhere the difference is about the exposure. When we can also have a UV exposure system, we can have electron beam which will help us in exposure, we can have just the optical setup for the exposure system. So this is what we have. So basically in this complex topic we have to study the concept of electron beam lithography also. That is we have a mask in which geometrical pattern will already be present, and we have to transfer this geometrical pattern onto the wafer. This is called lithography. So let us discuss it from very beginning and let us understand how it is taking place. Let's say I am having a silicon wafer of this dimension. So when I am having a silicon wafer of this dimension, this is wafer, and then at the top of this I will be having a silicon dioxide layer. So what I want to do, I require a wafer which will have a cut in this at this site, and then when there is a cut and I can remove this silicon dioxide away, and then this portion will be exposed and I can add anything which I want. So what the end result is, I want silicon dioxide to be removed. Now at this plate, at this position, when the wafer is exposed directly, I want to add some dopant. Let's say this is p type, here I want n type. So this is the required thing. So what I will do, this is the wafer, this is the silicon dioxide, I will put a mask on the top of it, and the mask will be selectively opaque and it will allow the exposure system only at a specific point. So let us discuss about what this mask will do. Let us allow the sunlight to enter. So this sunlight will enter, but this sunlight will not enter through the portion where it is opaque. So if I now coat my silicon dioxide with a sensitive material, let's call it photoresist. Let's call it photoresist. I'm coating this, and this photoresist have some reaction capability with the exposure system. For example, let us imagine a situation where it happens like whenever the sunlight is falling on the photoresist, it becomes very strong and robust, means it becomes unwashable, and wherever the sunlight has not reached, that portion becomes more soluble. So what will happen when I am going to wash it? More soluble portion will go off, and then the less soluble portion will remain as it is. So what is the next thing which I will get here is, this is my wafer. At the top, the complete silicon dioxide will be there, and then after washing, I will have photoresist only in this and only in this. This will be the only portion where I will have the photoresist, because the photoresist is a photosensitive material which has, taken its shape after the exposure was there. The portion where exposure was not there has been washed off. Now, I can see that still there is a layer of silicon dioxide which is stopping me to, go for diffusion and to go and create this N well. So I want this cavity, I want this clear space, I want the silicon dioxide to go off from this cavity. For this process, I will perform etching. Now, etching will only allow removal of silicon dioxide in the portion which is exposed. So what will be, how the next picture will look like? The next picture will look like this. And of course, there will be photoresist at the top. So this complete thing has gone. Now we have a clear short space, and I can create a N well here. So this is what lithography is. This is what the process is. Now, when we talk about photoresist, there are two kinds of photoresist. One is positive photoresist, another is negative photoresist. So depending upon which type of photoresist we are using, there will be two kinds of photoresist nature in one. Either the exposed portion becomes more soluble and the unexposed portion becomes less soluble. So in this case, we can see that the exposed portion has become less soluble and the unexposed portion has become more soluble. So it depends which photoresist we are going to use. The technique was first used in 18th century. The concept of transferring the pattern was used in a stone plate on which the pattern was engraved. We put some ink or something on that engraved pattern and then press it down onto the paper where we want to transform the pattern. Now here we know that lithography means photolithography, and then we have a lithography where Greek word it comes from is stone. Stone means lithos and graphy means to have a pattern, to draw some pattern. So lithography means when we are using some stone and we are printing some pattern, that is lithography. And when the process is light enabled, we call it photo enabled, we call it photolithography. So the three components which we have here is, first one is mask, second one is photoresist, and third one is UV exposure system. So when I talk about this, mask is the one which was this one. So starting from here, this one is the mask, second is the photoresist, this blue layer is the photoresist, and then the UV exposure system. The third is green rays are the exposure system. Now, types of lithography. The process of lithography is classified according to the type of exposure system or radiations. So, we have optical lithography, we have electron beam lithography or X-ray lithography. Optical lithography, in optical lithography, the resist is called photoresist, which is sensitive to light and light waves that we can also use UV radiations. Electron beam lithography is a lithography where the resist is called electron beam resist. So, instead of photoresist, we have electron beam resist. Means we should use a material which should be sensitive to electron beam. So, this is the this topic is the point of concern, and this is the topic of this present lecture, electron beam lithography. Here the photoresist should not react on photons, and the photoresist should react on electrons, to be more specific. And in case we do not need a mask, in this case we do not need a mask. Direct writing is possible by simply using electron beam like a pen and blank the beam, the regions where we do not want the resist to be exposed in the beam. So, wherever we want the pattern to be engraved, the electron beam will be targeted, and wherever we want the pattern not to engrave, we will not put electron beam over there. So, X-ray lithography is nothing but optical lithography only, and instead of UV exposure, we are going to use X-rays. Now, electron beam lithography. As the device dimensions, you know, they are becoming smaller and smaller. Lithography resolution must be minimum, and the optical lithography is giving us up to a range of 0.5 micron. With the help of electronic beam lithography, it is possible to realize even less than 1 micrometer. So, it is maskless lithography in which the pattern can be, means we do not require a mask. If we talk about this system, this complete mask is not required in electron beam lithography. So, it is maskless lithography in which pattern can be directly written onto the substrate. It facilitates the automation of lithography system. So, there is a control system and it is not manual, it is all automated. And electron beam lithography gives better depth of focus compared to optical lithography. The resolution of electron beam lithography is not limited by diffraction, but the electron scattering on the electron beam resist. In electron beam lithography, we need an electron beam, that is very obvious. The electron beam is focused, and the beam which is being focused is having a diameter which ranges from 0.01 microns to 0.5 microns. It is focused on the substrate, and the focused beam is scanned over the substrate. So, of course, we will have a setup. Let's say we have a wafer here, and then we have an electron beam from here. Let's say this is a pen like source, and we will have some electron beam. So, we will use some setup so that this electron beam is confined. Electron beam is confined to a particular point where we want the pattern to be engraved. So, this is about focusing. We do not need any mask. It is focused on the substrate, and the focused beam is scanned over the substrate, much like the electron beam is scanned on the TV screen, and it is scanned electron beam is computer controlled. Now, the focused electron beam is moved on the semiconductor substrate, and this movement will be depending upon the pattern that we need to write on the semiconductor substrate. If it is on the electron beam, resist will be radiated, and it will change the property of resist, of course. And if the focused beam is off, then the electron beam will not react with the resist, and it is not irradiating the resist. Now, if we talk about resist, electron exposure of resist occur through bond breaking. So here is a case of positive resist, or formation of bonds on cross links between polymer chains. So this is a case of negative resist. So positive electron beam resist gets softened. So we have discussed this before also, depending upon the positive photoresist and negative photoresist. Here also same case. So positive electron beams resist gets softened when it is irradiated by the electron beams, and the negative electron beams gets hardened, means it will not wash off when they are irradiated by the electron beam. So we can also see the mask generation here. A reticle is a special type of photomask where the data is only a part of final exposure area is present. A reticle is loaded in the stepper or scanner system where the multiple exposures are made in cover of full patterned area. So what we are actually trying to do here, we can see that the reticle is patterned with a machine which under computer control exposure and places pattern elements in the form of chip, image and 10 cross X scales. So we can see that there is a generation of 10 times reticle by electron beam pattern generator. So what is actually the purpose of electron beam pattern generator? It will create a step reticle with 10 times 10x reduction camera to make the master mask, and then we will have a copy of contact printing. So another way we have a we can generate master mask directly with electron beam, and this will be 1 times or 5 times of reticle, and then we can have a copy of contact printing. From here we can see. So here in this diagram we see electrons. Here is a setup which we have discussed before also, and like I was trying to pictorially represent electron beam lithography here only. So the same setup has been discussed in a proper and neat and clean labeled diagram. We can see that at the top notch we have an electron gun, and we also call it pen. So this pen will have a electron beam source, and then we will have a anode here. So what this anode is actually doing? The scattering of electrons are confined now. So this no more scattering is taking place, and then the electrons will follow. Electrons will fall down into a particular pattern. So what this actually helps? This helps us to getting a better focus on the substrate or on the wafer. So what is actually happening here? This anode is helping. We can see that before this green layer, all the electron beams were scattered like this, and now after this anode, these are very straight and these are very focused. Now we have magnetic lens here. Now after the passage of magnetic lens, what this magnetic lens is doing? Magnetic lens is trying to attract and contract the electron beams, and we are initiating the process of focusing. After this, it will go only narrow. So it will narrow down, and it will reach the exact destination, and this precision control is up to the layer of microns. We can understand this precision level of electron beam is less than level of 0.1 microns. So this magnetic lens is further converging it. We can see that this magnetic lens is further converging, so that when we have a base at the top, when we have a base at the bottom, we are very much pinpointed that we want the lithography to take place only at site A. So for this purpose, we are also using scanning coils. We can see in this diagram, we are also using scanning coils. These are the scanning coils. So scanning coils are nothing but they are helping us in converging only. Then we have back scattered electron detector. So back scattering means it stops and it helps in focusing. Stop back scattering and it helps in focusing. Then we can see we have a secondary electron detector also, and we have a input to the TV scanner also. So this is a complete automated system we can see in this diagram. Electron produced by the electron gun, which is taking place by the process of field emission or thermal emission, and the emitted electrons are accelerated by a high voltage, that is 10K to 100 kV. Electron beam is focused by magnetic lenses. We are using this magnetic lens to focus the electron beam. Beam scanned over the sample by deflection coils. So further scanning can be done using the help of with the help of deflection coils, and scattered or transmitted electrons are detected, and then particular focusing of the beam on the site A, let us say this is site A, is being achieved. So this is a process of electron beam lithography, where we can see that proper electron beam resist, whether it is positive or negative, is helping us to focus only at the particular spot and to achieve a precision and lithography up to a level where it is less than 0.1 micrometer. Now in this diagram we again have a pictorial representation of the projection system, and how we can see that in the previous diagram we have shown how anodic plate is helping us in doing so. Here we have a cathode at the top, and then using the grid we are allowing the electron beam to disperse through, and after the dispersion we have an anode here. Then what is actually happening with the help of magnetic lens is being told here with the help of first lens condenser. So actually the electron scattering and the proximity effect can be studied here. What is actually shown in this diagram? We have a substrate here. On the substrate we have a real resist image. So the real resist image means the resist which we are using in this prototype is shown here. Now at the top we are having a electron beam. We can see that this electron beam is focused and this is the direction of scan. So when we are focusing this electron beam, we can see what is actually happening here. We can see that the electron beam is removing the required substrate from the wafer, and accordingly the resist is helping to clear the substrate only at the desired place, and depending upon the scan, or depending upon the reticle which is available to the control system, depending upon the reticle which is available to the control system, the electron scattering will only take place at the point where electron beam is focused, and electron beam will be focused only at the point where the required N well or P well needs to be created. So we will study, we have to see now what is the role of electron beam resist, which are also the organic materials. They are basically the organic polymers. They are basically the organic polymers where we are having . irradiated, either of the two things can happen. That is, either the molecule of the polymer can break, that is called chemical bond breaking, or else they can form more bigger molecules, or we can call it cross linking, making the complete setup a three-dimensional setup. So either of the things will take place, either the polymer will break or the cross linking will take place. So this is what electron beam resist has a property of organic material. If these organic molecules, in these organic molecules, the monomer chains, that is nothing but the cross link chains, and become bigger molecule chains, and then obviously the molecular weight is going to increase, and then the molecular weight will increase, and it becomes difficult to dissolve them in developer solution. So the negative photoresist hardens, or it becomes irradiation. So when the incident electrons will have certain energy, or it will have an energy which is greater than the energy of bond, there is a situation which takes place where the bond breaks, and both the bonds, like they have to overcome the electron beam will overcome the energy which was required for the formation of bond. So which this process predominates the determine whether the resist is positive or negative. So we have also discussed the positive, and once again I'll discuss the concept of positive resist and negative resist. Electron exposure of positive of resist which occur through bond breaking is here positive resist, or the formation of bonds or cross links between two polymer chains. So this is a case of negative resist. So positive electron beam resist can soften when it is irradiated by the electron beam, and negative electron beam resist gets harder when they are irradiated by the electron beam. Upon irradiation, crosslinks of monomer chains are taking place, and therefore the molecular weight is increasing, therefore it becomes more difficult to be dissolved. So therefore negative photoresist is getting hardened on irradiation. On the other hand, when we talk about a case of positive electron beam resist, where the breaking of a chemical bonds are taking place, the chains are breaking and the molecular weight will only reduce, and therefore it is easier to dissolve them in the developer solution, and therefore the photoresist and the positive electron beam resist are softened upon irradiation. So these two are the major factors which play importance role, and they are like the limiting case of resist reduction, swelling of the resist which is blurring the feature size, and the developer and the electron scattering system, where we have in this lecture we have studied the process of lithography. In the process of lithography, we have come across the need of lithography, which was nothing but to transfer a geometrical pattern from the mask to the wafer. This mask will already have the geometrical pattern which we want on the wafer. So the process of transferring the pattern present in the mask is lithography. In lithography, we have kinds of lithography, where in this we have studied electron beam lithography. And other than electron beam lithography, we have photolithography and optical lithography. In photolithography, we have a resist which is reactive and which is sensitive to the presence of photons. So in the presence of when the photoresist gets exposed to sunlight, it can be two cases like positive and negative. In the positive photoresist and in the negative photoresist, in both of the cases, the exposed portion becomes soluble and the unexposed portion becomes insoluble, and vice versa. So we can wash and we can remove the excessive silicon dioxide by a process of washing and then etching. After etching, we get a clean short cavity. In that cavity, we with the process of ion implantation or diffusion, we add the dopants, and my next lecture will be nothing but ion implantation only, where we will be adding the dopants at particular sites. And after we have added the dopants, we can remove the extra photoresist, and we can straight away strip out the extra photoresist. So that was all from my side on electron beam lithography. We will discuss about ion implantation, the next complex topic, in next lecture. Thank you.